Hello everyone. Today we shall discuss displacement method. Displacement method is a very easy method to find out the focal length of a converging lens. This method is usually used in laboratory to find out the focal length of a converging lens. Let us see what is it. What we need here to conduct this method? We need one object and a screen. That's all. With the help of these object and a screen, we can easily find out the focal length of the experimental converging lens. Okay, suppose this is an object. This is an object placed here at this point P. Suppose this is an object placed here. And here is a screen which is placed at a distance d from the object. From this object, the screen is placed at a distance of capital D, suppose. Okay. Now, we place that experimental converging lens whose focal length has to be found out in between this object and the screen. Here, suppose here, I am placing that here, this converging lens is being placed here. And by adjusting its position, by just moving it towards right or left, we have to find such a position for the converging lens such that the image, a very sharp image of this object placed at P is formed on the screen. Okay. So basically what we need to do, we need to find out the location of the lens for which a very sharp image of this object is formed here. A sharp image is formed here on the screen. Okay. So suppose the distance from the object to the lens is u here. For this u, a sharp image is formed here. Okay, understood? Remember, the object and the screen is kept fixed. So this is fixed and this is fixed. You cannot move these two. Okay, the object and the screen is not moved here. Clear? So let us say this is u, the object distance from the lens, and it is v, the image distance from the lens here. Okay, so what can we do here? We can apply this in the lens formula. And what is the lens formula for us? That 1 by v minus 1 by u is equal to 1 by f here. Okay. So what can I get from here? That u is negative here because the object is placed on the negative side. So u is negative here. U is negative here, and v is positive here. So let us just put it here. So 1 by v minus 1 by minus u is equal to 1 by f. Okay. So here again we can write from here that u plus v makes d. So v can be written as d minus. We can write like this. Then replace the value of v here in this equation, and it gives us 1 by d minus u plus 1 by u as 1 by f is equal to 1 by f. So let us add here. So this gives us d minus u into u to u plus d minus u is equal to 1 by f here. So this u goes, and here it remains d upon d minus u into u is equal to 1 by f. Okay. So now this gives us d upon du minus u square is equal to 1 by f. Clear? So this gives us du minus u square is equal to df. Okay, what can I write it here? What I am getting here, that it gives us an quadratic equation u square minus du plus df is equal to 0. So this is what? This is a quadratic equation. This is a quadratic equation. So here I can find two values of u. So u can be here. U can be written as u is equal to d plus minus d square, applies Sridharacharya formula, d square minus 4df upon 2. So we can see u has two values. Let us say the one value is u1, that is d plus d square minus 4df upon 2, and the other value is u2 is equal to d minus d square minus 4df upon 2. So now what can we say? That u has two values. U has two values. One is u1 and the other one is u2. So here this position u, so if this is u2 or this is u1, there must be another position. There must be another position for which, another position of the lens for which there will be a sharp image on the screen for this of this object. So if this is u1, suppose if I say if this is u1, then this must be u2. Okay, and what is this gap? To find out the second position, if I need to shift this lens x along this axis, then we can say u2 minus u1 is equal to x. Okay, so let me write it here. How did I what was the values of u2 and u1? So the difference of the roots of u, let us say that is root over, you see that the difference of the roots will be d square minus 4df. This was the difference, and this is equal to x. So I can say that this x square is equal to d square minus 4df. So 4df is equal to d square minus x square, and f is equal to d square minus x square upon 4d. Look at this thing. To it, this is the focal length of the experimental converging lens. And what is on the right hand side of this expression? D, 4D, which is known to us, the distance between the object and the screen. And what is x? X is another factor here. X is the shift between the lens. X is the distance between the two positions of the lenses for which sharp image is getting formed here on the screen. Okay, so here using this formula we can easily find out the focal length of the converging lens. Notice here there's a very important thing to notice here, that what was the value of u? If I write down the value of u, look at, just rewind the video a bit and see that the value of u was d plus minus root over d square minus 4df upon 2. Now look at this thing. If suppose if d square would have been less than 4df, then this part would have been imaginary. So the value of u1 and u2 would have been imaginary. So there will not be any real image on the screen, because to have a real image on the screen, that image must be a real one. But the positions, the u2 and u1 would have been imaginary here. So in order to have a real image on the screen, at least in order to have a real image on the screen, d square minus 4df should be at least equal to or greater than 0. So d square should be greater than and is equal to 4df, or d should be equal to or greater than 4f. So what can I conclude here? So the minimum distance between the object and the screen is 4 times the focal length to obtain a real image on the screen. That is actually the principle of this displacement method. Okay, I hope you understood. So the formula for finding out the focal length of the converging lens is this: f is equal to d square minus x square upon 4t. From this result, we actually get some very interesting conclusion, and one of this, let us see, conclusion one of this, let us see. Suppose for u1, what is the value of v1? So v1, we know that v1 is equal to d minus e1. If the value of u1 is taken like this, the d minus d by 2 plus d square minus 4df by 2, then it will give me a value of d by 2 minus d square minus 4df by 2. So this is what? This v1 is equal to d minus d square minus 4df upon 2. Look at this very carefully. What is that? This is actually u2, isn't it? This is actually u2, the second value of u. Okay, now look at this. For u2, if I want to find out the value of v2 here, so what is v2? v2 is equal to d minus u2. So this is equal to d minus, what is the value of u2? d minus d by 2 minus d square minus 4df upon 2, and that gives us the value of d by 2 plus, this is 2 here, I missed it here, d square minus 4df upon 2. What is this? This is the value of u1. Okay, so for u1, if the object distance is u1, then the image distance is u2, and if the object distance is u2, then the image distance is u1. So here the positions, we can conclude that the positions are interchangeable. Conclude that the positions are interchangeable. That means we can say it in another way. Suppose this was the position, this is the position of the object, suppose, and if lens is kept here like this, and if here, suppose 10x here is the object distance here, and y is found out to be the image distance here, then in the second place, then in the other place of the lens, y will be the object distance here and x will be the image distance here. Things will be interchanged. Y will be coming here and x will be coming here. See, for u1 object distance, image distance was u2, and when u2 is the image object distance, u1 is the image distance. So here we can conclude that the positions are interchangeable. Now the second conclusion that we can find out from here, the second conclusion, that what is the magnification for the first case, for the first position of the lens, that is m1 is equal to what? v1 by u1. Okay, and what was the magnification for the second position of the lens? m2 is equal to v2 upon u2 according to the formula that you already know. So what is it? m1 multiplied by m2 is what? v1 upon u1 multiplied by v2 upon u2. Okay, and what is that? Because we know u1 is equal to v2 and u2 is equal to v1, so those things will be cancelling out each other, so that is actually 1, because we know that for u1, okay, so these two things are equal. Clear na? Because we know that v1 is equal to u2 and v2 is equal to u1, that you already know. We proved it. Okay, so this gives us the value of m1 into m21 to be 1 only. So what is m1? m1 is the magnification, that is height of the, we can write it from here, height of the object by height of the image 1, suppose, multiplied by height of the object upon height of the image 2. What is image 2? The height of the image formed when the lens in the position 1. And what is hi2? Height of the image when the lens is in the position 2. So that is equal to 1. Okay, so I can conclude from here h0 square is equal to hi1 multiplied by hi2. So h object is equal to root over hi1 multiplied by hi2. That is the thing that we can conclude from here. Okay, so that is all about the displacement method. Using this method in laboratory, we can easily find out the focal length of a known converging lens. Thank you everyone for watching. Let's meet in the next video.